All right, so in this example, we're going to show you how to use the tangent modulus method to look at inelastic buckling. So in the problem statement, it gives us some key information. So we're first given the length of the column, right, which is around 0.25 meters. We get that the column is a pinned end condition. So we can know that the K value, the K constant, will be equal to 1. And it's given that it is a rectangular cross-section column with these dimensions here, right? It also gives that the pin that if bending occurs, it will occur about the smaller second moment of area. So moment of area is just equal to 1/12 base times height cubed. So in this case, smaller h will give us a smaller I. So in this case, therefore, h is going to be equal to 0.025 meters or 25 millimeters. Right? So this next bit of information that the problem state gives us is that the column is made of a material for which the compressive stress strain curve is given by table 7.6.1. So here's our stress strain data, and it's also plotted in this graph here. All right. So what it asks, the problem asks us to do is to determine what the critical load of buckling is. So the first thing we need to do is to see what the Euler load is, or the critical stress for Euler's method. So we're going to use this equation here, and we're going to use all of our given constants from the problem statement to solve it. All right, so we're just plugging in all those values here, and what we'll end up getting is we'll get the critical stress will be equal to 1645 megapascals, which is a lot larger than the yield strength of the material, which occurs around 200 megapascals. So if we look at the stress strain curve, it starts to become nonlinear around 200 megapascals. So we can say that's our yield point. So because we have a much larger critical stress than our yield stress, we need to use the tangent modulus method to account for the yield stress, or the critical stress. So what we can do to use the tangent modulus method is, the first thing we need stress as a function of strain. So what we're going to do is we're going to take we're going to do a curve fit of just the inelastic portion here. So we're just interested in the inelastic region. So we'll take a fit of that using a polynomial fit. So we're going to use a 6th order polynomial. And if we do that, we'll get 6 values of coefficients. So we'll have C6, C5, C4, C3, C2, C1, and then some constant that's not a coefficient. All right, so to find the tangent modulus, we need to take the derivative of this function with respect to epsilon. So all we're basically doing is we're multiplying the coefficients by the exponents of the old system. So it's just going to be 6 times 6, C6, 5 times C5, 4 times C4, 3 times C3, 2 times C2, and just C1, right?